Thank you for the opportunity to share our research with you all here at the StatFizz. My name is Javier Rodriguez Laguna from UNED, Spain, and the title of my talk is Entanglement over the Rainbows. Let's start with a question. Can we engineer a one-dimensional quantum system whose ground state presents maximal left-right entanglement? Let us consider two identical sites and a fermionic particle jumping back and forth between them. The sites can be two nearby atoms or two cells of an optical lattice. This is the Hamiltonian for the fermionic particle, where these symbols represent fermionic operators, and the constant J0 stands for the hopping amplitude. Let the fermionic particle be in its ground state, which can be written like this. Please notice that this state is maximally entangled. In fact, it is a bell pair. Now let us add two more sides, to the left and to the right, and link to our system with hopping amplitudes which are substantially lower than J0. Call them J1. It can be shown that the ground state of our fermionic particle will remain approximately the same. What will happen if we add a second particle? In order to provide an intuitive picture, let us imagine that we place this second particle on the leftmost side. In order to minimize its energy, the particle will attempt to jump to a central site, but half of the time it cannot because the site is occupied. Let us not forget that the associated time to this process is large because the associated energy is low. If we wait long enough, though, the particle will manage to sneak into this site when the first particle is on the right side. The original particle cannot continue its happy jumping back and forth, so in order to minimize its energy, it will hop to the rightmost side. Since both particles are indistinguishable, we have effectively witnessed an effective hopping event between the two extreme sides, which has an associated hopping amplitude of J1 squared over J0, as it can be readily obtained using second-order perturbation theory. This approximation is usually known as a strong disorder renormalization group, or SDRG, but it is really more related to inhomogeneity than to disorder. The procedure can continue, and we can add more sides and more particles. If the hopping amplitudes decrease fast enough leftwards and rightwards, the ground state will be formed by valence bonds connecting symmetrically placed sides, hence the name rainbow for this state. So returning to our original question, can we design a local one-dimensional quantum system whose ground state presents maximal left-right entanglement? The answer is yes. A free fermionic chain, also known as a tight binding model, at half filling, whose hopping amplitudes decay as the exponential of minus hx from the center, will achieve maximal left-right entanglement in the limit in which h goes to infinity. As an aside, please excuse me for dropping irrelevant factors during this talk. My aim is just to highlight the main features of the model. The technical details can be read in our articles. The described system was termed a rainbow state by our group in 2014 because of this shape. The analogy goes a bit farther though. The energy of each bond decays very fast as we move outwards, so we can color them purple, blue, green, yellow, and red. Red for the outermost one, of course. In general terms, the energy of the last bond decays exponentially with the system size, the exponential of minus hn. Therefore, the energy gap is extremely low, and thus a finite temperature will overcome it and destroy our beautifully built entanglement. In practice, only the bonds whose energy is larger than kT will survive. The question should be therefore modified. If we can cool a 1D system down to a certain temperature T, how much left-right entanglement can we build? The deepest results in physics are typically prohibitions. You shan't send information faster than light. You shan't pass heat from a cold to a hot body without producing further changes. Well, it looks like there is a principle of the sort lurking around here. Large entanglement in a ground state leads to low energy gaps and therefore to low stability. In fact, there is a rigorous result pointing in this direction, Hastings' theorem. It shows that if a local windy Hamiltonian presents a finite energy gap in the thermodynamic limits, then its entanglement entropy will saturate with size. This result is linked to the area law, whose depth is hard to overestimate. This rainbow phenomenon is not at all exclusive of fermionic chains. We have shown it also in Heisenberg and Ising chains. In fact, it can be seen as a generic consequence of conformal invariance. If the low energy behavior of a Hamiltonian of this form is described by a certain conformal field theory, CFT, then a similar theory with a smooth modulation of the prefactors like this will be described by a rainbow system, assuming a small value of h. We see that the associated CFT lives in a metric of constant negative curvature, except at the center. This conformal interpretation also works when we introduce a small mass parameter, and in fact, in that case, the rainbow effect is confined by the correlation length. Let me describe now a few of the most intriguing features of the rainbow system, both for small and large values of h. First of all, the rainbow state is a thermophile double for a homogeneous half chain. Let us see what we mean by this. If we just retain the left half of the rainbow system, the system must be described by a reduced density matrix of this form. The operator that goes in here is called the entanglement Hamiltonian, and for reasons that I will not describe here, it corresponds to the clean CFT Hamiltonian to a very good approximation, with a temperature given by h by 2 pi, which bears a strong resemblance to the a by 2 pi temperature associated to the Unruh effect. Here we can see a row of the correlation matrix of the thermal state at temperature h by 2 pi using 20 sites, compared to the correlation matrix of the rainbow state with 40 sites and the same h. Thermophile double states are extremely relevant for black hole physics and for quantum technologies, where they can be employed to build teleportation machines. Second and last, I want to call attention on the folding effect. The rainbow chain behaves as if the chain folds around its center, becoming a ladder. Indeed, as h grows, this side talk less and less to its neighbors along the ladder, and the left and right sides, and more to its partner along the rung. In this sense, we can say that the rainbow state presents short-range entanglement in a different space-time topology. We can even tune this effect up by introducing a spare site at the center of the chain, thus inducing a symmetry-protected topology phase. Moreover, we can tune the central hopping up or down, and we will observe a threshold above which the rainbow effect is suddenly lost, i.e. an entanglement transition. The folding effect led us to devise a new tool to determine the underlying topology of a quantum many-body state. Indeed, the entanglement structure of a given quantum state can be approximately summarized into a matrix containing the so-called entanglement links Jij, such that the entanglement entropy of any block A can be written as a sum of the links connecting sides of A with sides of the complementary set. This analytical tool provided further insights into the dynamics of the rainbow state, but let us leave this part here. During this short talk, I have just scratched the surface of the rainbow system. My aim was mainly to intrigue you, so as you take a look at our papers in a convenient page that summarizes our progress since 2014. All this work has been done by a large team, mostly, but not only, in Madrid. Among the most relevant collaborators, we find Germán Sierra, Silvia Santalla, José Enrique Alvarellos here in Madrid, my former PhD students Giovanni Ramirez, Nadir Samos, and Begoña Mula, Eric Toni and Pasquale Calabrese in Trieste, Jérôme Dubeil in Lorraine, and last but not least, Sudipto Singaroy, now in Trento. So thank you very much for your attention.